Greetings and welcome to Distiller. In the last class, we discussed certain concepts in chemical engineering like ideal gas, partial pressure, partial volume, Amagat's law, Dalton's law. After that, we discussed a very important uh, result that mole percent is equal to partial pressure percent, which is equal to volume percent. And then we did a problem in which we calculated the average molecular weight of air. And after that, we calculated the percentage composition of air by weight. Yesterday, I taught you a very important concept as to how to convert mole percent to weight percent. So in order to convert mole percent to weight percent, I told you, first of all, you need to take basis as 100 kilomole of your mixture. Based on that, you would get moles of individual components. Using moles of those individual components, you would be able to get masses of individual components by multiplying moles with molecular weight. So you would get mass of individual components. Using these individual component mass, you would get total mass. You would get total mass, which is the summation of all the masses. And after that, you would calculate weight fraction. Weight fraction is equal to individual weight upon total weights. All right. So this is what we discussed in the last class. Today, we are going to do certain more numerical problems on gaseous mixtures. So this is the problem that we discussed yesterday, and this is what we have done. Right? Now, this is the second example problem. Hope you are comfortable with the concepts that you have been taught. Now, this problem is the composition of natural gas given by weight, and we have to convert it into mole percent. In the last problem, we had to convert mole percent to weight percent. In this problem, we have to convert weight percent to mole percent. Okay, this is the second time. So in cases when you have to convert from weight percent to mole percent, you have to do exactly what you did for mole percent to weight percent, but this time you have to start with weight. So like in mole percent, we took 100 kilomole of mixture. Now we will take 100 kg of mixture. When you do that, then you will be able to get individual masses, right? You will be able to get masses of individual components, right? Then when you divide mass by the molecular weight of individual component, you get moles of the individual components. You get moles of the individual components. After that, from moles, you are going to calculate total moles. And then you're going to calculate the mole fraction. So we know that mole fraction is equal to individual mole upon total moles. All right. So again, if you have to convert from mole percent to weight percent, then you have to start with basis as 100 kilomole of mixture. All right. If you have to convert from weight percent to mole percent, then you have to start with basis of 100 kg of mixture. All right. Then Using this basis, you can calculate individual masses. All right. Using this, I'm so sorry. Using this, you will calculate the individual moles. Since this is 100 kilomole of mixture, you will get individual moles. And using this, you will be able to calculate the individual mass. All right. Then from individual moles, you can get individual mass by multiplying moles with the molecular weight. Similarly, using individual mass, you can get individual moles by dividing the individual mass by the molecular mass. All right. Then using individual mass, you are going to find total masses. Using individual masses, you're going to calculate the total mass. And similarly, using individual moles, you're going to calculate the total moles. All right. After that, from once you get the total mass, you can get the mass fraction or the weight percent. Similarly, from here, you can get the mole percent. All right. So this is what you need to do, the procedure to be followed if you have to convert from mole percent to weight percent. And this is the procedure to be followed when you have to convert from weight percent to mole percent. All right. So now in this example, we need to convert everything from weight percent to mole percent. So what we are going to do is we are going to take each component. So our components are methane, ethane, hydrogen, carbon monoxide, and carbon dioxide. All right. Then we are going to keep our basis. Since we have to convert everything from weight percent to mole percent, that is why the basis is going to be weight, that is 100 kg of, what is the mixture? Natural gas. So 100 kg of natural gas. All right. Then since we have components, we have each of the components, and we have the weight percent of each of the components. So we only have to write down the same weight percent, that is 70.9 kg. This is going to be 5.1 kg. This is going to be 3 kg. This is 15 kg. And this is 7 kg. All right. Then once you get the weight, this is going to be your step number 1. Get weight. All right. Then once you get weight, then step 2 is to get the molecular weight. So the molecular weight of methane is 16 kg per kilomole. Ethane is 30 kg per kilomole. Hydrogen is 2 kg per kilomole. Carbon monoxide is 28 kg per kilomole. And carbon dioxide is 44 kg per kilomole. All right. Then next step, if this would have been mole percent to weight percent, then we would have calculated weight in the next step. But this is weight percent to mole percent. That is why we are going to calculate the moles in the next step. So we are going to get moles over here. All right. So my moles are weight upon molecular weight. All right, weight upon molecular weight. So 70.9 upon 16, that is 4.43. This is 0.17. This is 1.5. Then this would be 0.536. And we would finally get 0.16 over here. All right. Hence, using these, the next step is to calculate the total moles. Okay, so total moles are 4.43 plus 0.17 plus 1.5 plus 0.536 plus 0.16. That is 6.796. All right. Then we have to calculate the mole fraction. So mole fraction is nothing but individual moles upon total moles, right? So individual moles 4.43, total moles 6.796. So 4.43 upon 6.796, that is 0.652. All right. Similarly, 0.17 by 6.796, that is going to be 0.025. Then 0.221. This is 0.079. And finally, this one is 0.023. All right. Now, once you get the mole fractions, you must add them up always and see if you're getting 1. Because if you're not getting 1, then you've done some error in the calculations. So you need to rectify it. But I have got 1 over here. So there are no errors in my calculations. Then I need to calculate mole percent. That is nothing but mole fraction into 100. All right. So this is going to be 65.2%. This is 2.5%. This is 22.1%. This is 7.9%. And this is 2.3%. And the total is going to be 100%. This is your answer. All right. So hope you people are clear about the steps involved in converting weight percent to mole percent. So once again, let me tell you, in order to convert weight percent to mole percent, we need to take our basis as 100 kg of mixture. Then from this basis, we'll get individual weights. Using individual weights, we are going to calculate moles, individual moles. All right. Weight upon molecular weight. All right. Then using individual moles, we are going to calculate total moles. And using total moles, we are going to calculate the mole fraction. All right. Mole fraction is equal to individual mole upon total moles. All right. So this is the problem number 2. Now we have another problem. Go ahead, pause the video and try to solve this problem yourself. For those who have solved the problem themselves and got the answer very well, and for those who have not been able to solve this problem themselves, now we are going to do this problem. So let's see. All right. So we have a mixture of nitrogen, oxygen, and hydrogen gas kept in a 900-liter tank. This is the total volume. This is the total volume. All right. The weight percent of nitrogen and oxygen are 35% and 28% respectively. Remember, weight percent. Calculate the average molecular weight of the mixture and also calculate the partial volume of each component. Now, Let's see how to do this problem. So we have our components. We have our components, nitrogen, oxygen, and hydrogen. All right. Then we are going to take basis as 100 kg. 100 kg of mixture. All right. Now, they have given us the compositions in weight percent. Okay. So we'll get weights. So weights are going to be 35, 28, and hydrogen is going to be 100 minus 35 minus 28. That is 37. This is going to be the weight. All right. These are going to be the weights of the individual components. Now, in the question, they have asked us to calculate the average molecular weight. Remember, average molecular weight is nothing but summation of product of mole fraction into molecular weight. So we need mole fraction, right? What here we have is the weight fraction. So mole fraction is necessary. That is why we need to do our conversion from weight percent to mole percent. Hence, the step one is to take basis as 100 kg of mixture and calculate the weights. All right. Once we have got step one, then our step two is to get the molecular weight of each component. So molecular weight of nitrogen is 28, oxygen is 32, and hydrogen is 2 kg per kilomole. All right. Then the next step is to get moles. All right. So moles are weight upon molecular weight. So that is 35 upon 28. That is going to be 1.25. This is 0.875. And this is 18.5. All right. Then the next step is to calculate the total moles, right? So total moles are going to be 20.625. All right. Then the next step is to get the mole fraction. So mole fraction is nothing but individual mole upon total moles. So individual moles are 1.25, total moles are 20.625. Hence, we'll get mole fraction of nitrogen as 0.061. Similarly, we'll get mole fraction of oxygen as 0.042. And mole fraction of hydrogen is going to be 0.897. All right. When we add, we'll get 1. All right. So our mole fractions are correct. Once we get the mole fraction, then the first part of the problem can be solved. That is, calculate the average molecular weight. So average molecular weight is nothing but summation of product of mole fractions into molecular weight, right? So that is 0.061 mole fraction of nitrogen into molecular weight of nitrogen plus mole fraction of oxygen into molecular weight of oxygen plus mole fraction of hydrogen into molecular weight of hydrogen. Hence, we'll get the average molecular weight as 4.846. All right. Unit is kg per kilomole. So the first part of the problem is solved. Next, they are asking to calculate the partial volume of each component. Now we know that for a gaseous mixture, we have mole percent is equal to partial pressure percent is equal to volume percent, right? Hence, we'll get mole fraction is equal to volume fraction, correct? That means yi is going to be partial volume of ith component upon total volume, which implies the partial volume of ith component is going to be mole fraction into total volume. All right. Now they have given total volume to be 900 liter. All right. So in order to calculate the partial volume of each component, we simply have to multiply the mole fractions by 900. All right. So this is going to be 0.061 into 900, which is 54.9 liter. Then this is going to be 0.042 into 900, that is 37.8 liter. And finally, this is going to be 0.897 into 900, which is equal to 807.3 liter. All right. Once again, add all these and see if you are getting the total volume. Hence, when we add all these, we'll get the total volume. Hence, from here, we can also verify the Amagat's law of Amagat's law of additive volumes. All right. So hope you're clear with this problem. We had everything in weight percent. That is why we converted into mole percent. Once we got everything into mole fraction, then we found the average molecular weight, which is equal to summation of products of mole fraction into the molecular weight. And finally, we got the partial volume of each component by multiplying the mole fractions by the total volume. We used the rule mole percent is equal to partial pressure percent is equal to volume percent. Then we move on to example number 4. Read the example, pause the video, and try to solve this example yourself. Hope you've been able to solve this problem yourself. If you haven't, then let's solve it. All right, I have nothing. Wait. Yes. So to solve this problem, we have our components. First, let's read the problem. A mixture of 10% methane, 25% carbon dioxide, 50% hydrogen, and rest oxygen by mole is maintained at a pressure of 2 bar, all right, and temperature of 473 Kelvin. Calculate the density of the mixture and composition by weight. So let's do this problem. We have to calculate composition by weight. That means we need to do the conversion from mole percent to weight percent. And we also need to calculate the density of mixture. So let's do this problem. So we have our components as methane, carbon dioxide, hydrogen, and oxygen. All right. Then we'll take basis as 100 kilomole, since we have to convert from mole percent to weight percent. Therefore, we are going to take basis as 100 kilomole of mixture. All right. So the composition is given to be so step 1 is to get the moles. All right. So to get the moles, we are going to have 10, 25, 50, and 100 minus 10 minus 25 minus 50, that is equal to 15. All right. Then next step is to calculate the molecular weight. All right. So molecular weight of CH4 is 16 kg per kilomole. Carbon dioxide, it is 44, hydrogen 2, oxygen 32. All right. Then we have to calculate the weight. Step 3 is to calculate weight. So weight is nothing but moles into molecular weight. All right. So this is going to be 160 This is going to be 1100. This is going to be 100. And this is going to be 480. All right. Next step, calculate the total weight. All right. The total weight is going to be 1840. You add all of these. So you'll get the total weight as 1840 kg. All right. Then the next step finally is to get the weight fraction, which is individual weight upon total weight. So it is going to be 160 by 1840. That is 0 0.087, 0 0.598, 0 0.054, and 0 0.261. All right. When we add, we'll get 1. All right. So this is my composition by weight. All right. This part of the problem has been done. All right. Now we have to calculate density. So density, I told you the formula of density in the last lecture. That is PM average upon RT. All right. Temperature is given to be 498. Pressure is 2 bar. That is nothing but 200 kilopascal. Okay. Into average molecular weight upon R into T. All right. So average molecular weight is nothing but summation of mole fractions into molecular weights. So that is going to be equal to 0.1 into 16 plus 0.25 into 44. 0.1 is the mole fraction of methane. 16 is the molecular weight of methane. 0.25 is the mole fraction of carbon dioxide. 44 is the molecular weight of carbon dioxide. Then 0.5 is the mole fraction of hydrogen. 2 is the molecular weight of hydrogen. And then 0.15 is the mole fraction of oxygen. And 32 is the molecular weight of oxygen. So when we add all of them, we get 18.4 kg per kilomole. All right. This is the average molecular weight. Hence, when we solve for density, we get density equals to 0.9358 kg per meter cube. Make sure the units are balanced. See, you have pressure in kilopascal. Just a minute. You have pressure in kilopascal. You have average molecular weight in kg per kilomole. All right. Then you have R in kilojoule per kilomole Kelvin. And as we discussed, kilojoule can be written as kilopascal meter cube per kilomole Kelvin into temperature is in Kelvin. So Kelvin, Kelvin, kilomole, kilomole, kilopascal, kilopascal. Hence, the unit of density is kg per meter cube. All right. That's all.